You finish the optics problem, check your math, and get an image distance of 30 centimeters. But your classmate did the exact same steps and got negative 30 centimeters. The pencil lead snaps. In ray optics, the most common point of failure doesn't happen when you're drawing the physical ray diagrams. The breakdown almost always happens when you try to assign positive and negative signs to those lines. Without a standardized system to track these positive and negative values, you are forced to memorize dozens of highly specific equations for every possible combination of concave, convex, real, and virtual setups. Instead of relying on rote memorization, we can replace all those distinct rules with a single geometric framework. Mastering this framework requires setting aside arbitrary rules. It is about learning to directly translate the physical paths of light into a reliable mathematical reality. The standard tool for this translation is called the Cartesian sign convention. The textbook definition of this convention looks like this diagram, showing how we measure distances and heights relative to a mirror or lens. The core premise is straightforward. We are taking a standard two-dimensional Cartesian coordinate plane and overlaying it directly onto our physical optical setup. This grid takes physical directions, left, right, up, and down, and converts them strictly into positive and negative algebraic integers. By forcing the physical setup onto this grid, you remove the guesswork. The resulting math will automatically calculate the exact physical position and orientation of your image. This set of rules applies universally to all spherical surfaces. It works whether the surface is curved or flat, and whether it reflects light or refracts it. The Cartesian grid standardizes the relationship between the physical world of light and the abstract world of mathematics. To build this system from first principles, we start at the origin. The geometric center of a spherical mirror, called its pole, or the optical center of a lens, must be locked exactly at coordinate 0, 0. All distances are measured from this single point. Next is the x-axis rule. The direction that the incident light is traveling dictates the positive horizontal direction. If light travels from left to right, the right side of the axis is positive. Conversely, any measurement taken against the flow of incident light dictates a negative horizontal direction. For the y-axis, heights measured upward from the principal axis are universally positive, and heights measured downward are strictly negative. By locking the optics to these axes, the problem transitions from a subjective sketch to an objective mathematical graph. Be careful, though. If a specific problem places the light source on the right, traveling left, the positive axis flips to align with it. The light always sets the terms. The direction of incident light defines the entire mathematical landscape before you even pick up a calculator. Let's apply this framework to the object distance, represented by the variable u. Because the light travels from the object to the mirror, measuring the distance from the pole back to that object requires moving in direct opposition to the incoming light vector. Due to this geographic reality, the object distance u is universally assigned a negative value in standard setups. Now look at the geometry of the mirror itself to determine the sign of its focal length, f. Here we have a concave mirror. If we trace the measurement from the pole back to the focal point of this concave mirror, we are once again moving against the flow of light. This retrograde measurement dictates that a concave mirror's focal length is always a negative integer. But if we change the physical setup to a convex mirror, the center of curvature and the focal point shift to the space behind the reflective surface. Tracing the new measurement from the pole to the convex focal point means we are now moving with the light vector. That forward measurement dictates a universally positive focal length for convex mirrors. Many students simply try to memorize the phrase f is negative for concave, but that rote memorization breaks down quickly when setups change the light. Focal lengths and object distances are not arbitrary rules you need to memorize. They are inevitable physical measurements mapped strictly by the Cartesian grid. This brings us to the mirror equation. 1 over v plus 1 over u equals 1 over f. This single relationship replaces all scenario-specific formulas. By inputting a negative object distance u and a negative focal length f for a concave mirror, the algebra automatically resolves to find the image distance v. If that calculated image distance outputs as a negative integer, the math unequivocally proves the image has formed in front of the mirror. To find the exact size and orientation, we use linear magnification, m equal to -v over u. If the image points below the axis, the y-axis rule takes over. The height h' is negative, forcing magnification m to be negative. When translating that math back into reality, a negative magnification explicitly guarantees the physical image is inverted and real. This equation collapse works because the algebra and geometry are inextricably linked. The resulting numbers represent the exact physical coordinates of the image. Now we face the final challenge. How does this framework handle lenses, which bend light through a medium rather than bouncing it back? Replacing the mirror with a thin convex lens at the 0,0 origin, the Cartesian grid does not alter. We introduce the thin lens formula. 1 over v minus 1 over u equals 1 over f. It operates within the exact same geometric logic. The object distance is still measured against the incoming light, keeping it firmly anchored in the negative zone. This single, elegant convention successfully unites two entirely distinct physical phenomena, reflection and refraction, under one cohesive and predictable algebraic system. By mastering this single geometric framework, rather than memorizing isolated equations, you eliminate sign errors and establish the mathematical basis for understanding every optical instrument.